In our last video, we went through the process of logarithmic differentiation, and I said at the end of that video I'd put up the process we used. And then I forgot to do that. So at the beginning of this video, this is the process of logarithmic differentiation. We take the natural log of both sides. Then we implicitly differentiate both sides, remembering to treat y as a function on x. We solve for y prime, or dy dx, whatever we've chosen for the problem. And then at the end, we write both sides in terms of x. This is where we plug the original function back in for y. So let's do one more logarithmic differentiation example. And this will come with a bit of caution. This is the kind of problem where if the instructions are just find dy dx, right, take a derivative, I want to do the easiest thing possible. And it looks like it could be a logarithmic differentiation problem, but it's really easier to do as a factoring problem. Using the formula for the difference of two cubes, I can rewrite the top this way. And I realize I have common terms that can cancel. X minus 1 times x plus 1 is x squared minus 1, and now all I have to do is take the derivative and say, hey, that's 2 times x. And this was a problem on your last lab, and the hint was do some algebra first. Well, the reason I want to use this as a cautionary thing is because maybe now do some algebra first, you might think to use logarithmic differentiation. And so my advice would be to pay attention for factoring things, because those are often easier. But let's do this problem like it was a logarithmic differentiation problem just for the practice. So I'm going to assume that maybe I'm having a bad day and I didn't notice the factoring thing, or maybe the instructions just said use logarithmic differentiation, because it's always good to practice that skill. And so in my first step, I'd have to take the natural log of both sides. Most of the time when I'm doing this for myself, I go on and skip this part and just go on and write that out all expanded using the properties of logarithms. But for this video, I think I'll show all of my work. All right, so I've expanded that side and I'm ready to differentiate each piece. I'm ready to implicitly differentiate. I think if I was using logarithmic differentiation, I was paying attention to everything, I'd go on and factor that out. But my supposition at the beginning was maybe I was having a bad day and I'm stuck doing it this way because I didn't see the factoring trick. So I'm just gonna keep going with this and take the derivative of all of the pieces. So on the left-hand side, I have 1 over y times y prime. And then this would be 1 over x cubed minus 1 times 3x squared plus 1 over x plus 1 minus 1 over x squared plus x plus 1 times the derivative of the inside is 2x plus 1. Hey, I have a derivative. And so now I need to get y prime by itself, so I have y times all that stuff. So instead of writing the variable y, I'm just going to go on and write the expression, kind of solving for y prime and substituting back in one step. And following the process of logarithmic differentiation, I've arrived at my answer. And it's not a pretty answer. But if we got in here and distributed and did all of the arithmetic, did all of the algebra and canceled things out, we would get ... equals 2 times x. And this is the caution in using logarithmic differentiation when an easier method applied, because we might not think to simplify this and our derivative's as easy as 2x, and we'd be stuck using this expression here. So, logarithmic differentiation is great, but sometimes with expressions like this, we might want to do some simpler algebra first. So you might be thinking, is logarithmic differentiation actually ever necessary? Because even in our last video, we could have done a lot of algebra first and then just used the quotient rule. So in the next video, I'm going to do an example of a function where the only way in which to take its derivative is to use logarithmic differentiation.